IIT Bombay, and PhD from Nagpur University at VRC VNIT. He is working as a professor in Computer Science and Engineering Department, VNIT Nagpur, 25 years. He is also the Associate Dean for Information Technology, MIS, Network and Website. He is also Chairman of ACM Nagpur Local Chapter. He has more than 8 PhD students at VNIT Nagpur. He is the member of Board of Studies in various NITs and government engineering colleges in Maharashtra. He has completed many funded projects on various domains and areas. He has also executed many consultancy projects for Government of Maharashtra, India. He has published more than 8 books on Oracle and multi-dimensional modeling of data. His best-selling book is Oracle 11G SQL PLSQL programming. His area of interest is management system, data warehousing and mining, big data, pattern recognition, and machine learning. So now I request Dr. Parag Deshpande sir to start the session. Deshpande sir.
Hello. Is the presentation is visible to all of you? Or I think I have to share. So, good morning, everybody. Is the presentation is visible to all of you? Okay.
Yes, sir.
Okay. Now we'll start with the topic in machine learning, that is the dimensionality reduction. First, what is the meaning of these dimensions? Now, whenever there is a machine learning problem, then how we are going to solve this machine learning problem, or what are the different problems in the machine? For example, you are having the symptoms of the patient and you have to diagnosis, you have to make the diagnosis regarding his disease. So what data of the patient and
Deshpande sir, you
feed
can
it,
start the session.
right? Hello. From the historical data, and based on that we are making a model. That means we are going to have some classification model. So the machine learning problems, they includes the
So there are some connectivity issue at the sir end. So sir is investigating and he will trying to get connect. So just wait for 5 minutes, then the session will start.
Okay, now it is, I'm audible.
Yes, sir, you are audible.
Yeah, actually, that was some intermittent breaking of the internet.
Okay, sir.
I don't know what happened. Okay, so we were discussing the differential problem. So what we are having is we are having the set of features, right? And we are having the classes, right? So most of the machine learning problems, they are trained using the past data, using the set of features, right? And you may have the class labels, right? Or you may not have the class labels.
Sir, these are not visible.
Just a minute, just a minute.
Yes, sir.
Now it is visible.
No, sir.
Just a minute. What I will do is, because this window is, I will again start it.
Okay, sir.
PPT is visible?
Yes, sir. PPTs are visible.
Okay. And voice?
Yes, sir. It is also clear.
Okay. So we're discussing the typical nature of the machine learning problem. So in the machine learning problem, right, mainly the problems are classification, that is the supervised learning, right, or clustering, right, that is the unsupervised learning, right, or the prediction, for example, using the regression, right. So most of the machine learning problem, they are basically trained using the past data, and the past data is modeled using the set of features, right, and if it is a supervised learning, then using the set of class levels. For example, you want to build a patient diagnosis system, right, in which you want to classify the patient, right, this is as either typhoid or flu. So in that case, you will collect symptoms of the patients, right, and from the past data, and you know that that patient is suffering from the typhoid or flu, right. So you label that patient, right, as a typhoid or flu. So you may have the symptoms like headache, fever, right, or the cough, right. So you may have the different features. And based on that, he will make the model using the decision tree or support vector machines, right? Or maybe the neural network. Another example is you want to classify the image, right, into the English characters. Since it is basically the character recognition problem. Your input is the image, and you have to classify it as whether A, B, C, or D, right? So here, the image, right, it is modeled as the set of features. So if your image is of the size, say, 30 by 30, then you will have the 900 features, right? And you may have a class like character A, character B, right? So these set of features, right, they are called as the dimensions. Very often, if the model is not giving you the result, then you may tend to add the dimension, add more features, right, to make it more accurate. So based on that, okay, the new features, right, it will discriminate the class is more accurate. Then the question is whether adding the set of features will always results in more accuracy of the model. So what I am showing is the just introduction, right? I have not started it, the dimension reduction part. Right. So this set of features, right, they are typically called as the dimensions. Now you may have the dimensions, right, in the model or in the classification problem. That will range from, say, you may have the 4 dimensions or you may have, say, thousands of dimensions. So then the question is whether this very high number of model behavior or whether it will make a model more accurate or whether it will accuracy in the model. informational content. So it is better in that case to reduce or remove the dimension x2, right, of the data, because x2 is dependent on x1. So using the mathematical model, right, we should able to remove, right, all such dependencies, right, in the dimensions. Right, so these are some techniques, right, dimension reduction techniques, right. These are the mathematical techniques, right, in that direction. So now we'll see what is the effect of number of dimensions, right, in the data. So now this is the dimension.
Sir, your PPTs are not visible, also not clear.
Yeah, some data, they may not be able to represent the space, right, complete space, right, of the data. Now,
Sir, your PPTs are not visible.
There is no audio. Sir, we can't hear you.
Now it is okay?
Yes, sir.
Okay, are you able to see the slide?
Yes, sir. Yes, sir.
Okay. So in the slide, we are going to have the expression for the d-dimensional cube and d-dimensional sphere. So sphere means it is the sphere which is touching all the planes, right, of the d-dimensional cube. I will just check it. Okay, now it is visible.
Yes, sir.
Actually, what is happening when I'm using the full screen, right? There may be some connectivity issue with the WebEx. Okay, but just check it. Okay, so what you do is you just note down these two equations, right? One is the equation for the volume of the d-dimensional sphere, and second is the volume of d-dimensional cube. Now, for example, the d-dimensional cube means if you take the two dimension, it is just the your square, right? Of you can say the size of say or size 1, right, from both sides. And if you draw the circle, right, so that it will touch all the sides of the square, right, within that, and the circle should be within the square, right, then it is a two-dimensional sphere, right? So that circle is nothing but that, it's the two-dimensional sphere, right? So this is the generalized equation for the three-dimensional sphere and d-dimensional cube. And if you take the ratio of it, right, and as you go on increasing the size of the dimension, right, you will see that the this ratio tends to 0. It means what? The volume of the sphere as compared to the volume of the d-dimensional cube goes on decreasing. Now, the meaning is that all the space in the original d-dimension, when it is represented by the sample, then all the part of the spaces, they may not be represented, right, by the samples. And then that actually adds the challenges in making the model, right, in terms of the accuracy, and second, in terms of the completion. Now, another argument, right, is that if you take, right, the volume of the shell of the thickness, right, epsilon, that means they are in the two concentric circles, right, and the radius they are differing by say epsilon, right, then you will get this equation. And as you go on increasing the size of the t, right, this ratio tends to 1. It means that all the volume is mainly occupied by the shell. So that is another argument, right, for the space, right, in the d dimensions. Now, that is the one thing that the samples they fail to represent all the part of the spaces, right, in the d dimension. As this d grows, then the finite number of samples they were not able to represent all the part of the spaces. Another phenomena, right, in the very high dimension is concentration of norms and distances. Right. Now, what is the meaning of it? Is that the discriminative power, right, of the model, right, that goes on decreasing, right, as the number of dimensions it goes on increasing. So this is, right, represented by another mathematical equation, right? And if you see this equation, you will see that the angle between the dimension and the diagonal, right, it tends to move to 90 degrees, right, as the number of dimensions goes on. Right, in other words, the cosine value, right, of the diagonal and the dimension, right, it tends to 0 as you increase the number of dimensions. Now, the meaning is that it means that if any point, right, it is near to some dimension of axis, and when you project it on the diagonal, then it goes to the origin. Right? For example, if you are having a point on the x-axis and you project it on the y-axis, right, then you will get a 0, right, on the y-axis. So points which are near to x-axis, if they are projected on the y-axis, right, they are near to the 0 of the y-axis. That means any axis which is at 90 degrees, that is the x-axis, right, their value is going to be 0. Right? So all the points, right, which are near to one dimension, right, when they tends to, you tend to put it on the diagonal, right? Because why I'm saying the diagonal? Because diagonal is they are basically representing the separating planes, right, in the high dimensional data. So all their projections, right, on the diagonals, right, of the dimensional data, right, they tends to 0. And so since they are very cramped, right, on the diagonal axis, their discriminative power, right, goes on decreasing. So that is the two arguments, right, based on the domain. So that's why we have to reduce the dimensions. Now another phenomena in very high dimension is making the model. For example, if you are to take the classifier, right, then you are going to assume that, okay, the data is following certain probability distribution. For example, you can assume that, okay, the data is following the normal distribution. And based on the data, you will estimate the parameters of the distribution. That means it is the estimation, right? So the parameters may not be accurate, right? They are just estimated from the past data. If you increase the number of dimensions, then your number of estimated parameters, they goes on also increasing, and that will add the error, right, in making the prediction of the probability distribution. So that is the third argument, right? So that indicates that a very high dimensional data may not be much useful. So, and this is called as the curse of dimensionality. Right? Means the losing the discriminative power, right? If the number of dimensions or features are increased, right? Then your the accuracy of the model goes on decreasing. Right? This is called as the curse of dimensionality. So another practical point of view is that whenever the data is given, right, you have to visualize the data and in the high dimensional spaces. very difficult to visualize. So we have to visualize the data, right? Because the user, right, or the end users, right, they want to visualize the data, right, so that he can understand the data. So that is the other reason why the dimensions should be fixed. Then, if you are going to have a low number of dimensions, then naturally the computing power, right, required is also less. Right? So the low dimension data, it will decrease the computational
Sir,
time. Yes.
but the slides are not reflecting, sir. We are still on hyper volume of cubes and spheres.
Now it is visible or it is still not visible.
Visible, sir, visible. But still now we were stuck on the same slide. We were not able to visualize the content that you were teaching us about.
So it is still the hypervolume of cubes.
No. Now we have got into click to edit the title text format slide.
Now what you are seeing here, maybe hypervolume of the thin spherical shape. Now it is visible.
Yes, sir. But it is the first slide.
Right. That is the second slide.
Yes, sir. Second slide.
Third slide. Okay, now it is visible.
Sir, half is visible because the size is
Yeah.
increased to 150.
Actually, I zoomed it, right? Because the full slideshow is having some problem.
Okay, sir.
Right? So I will just.
Sir, you can convert in PDF and that PDF you can show, so that can be possible.
Sir, you can set the zoom level to 100%, sir.
But for some people, that 100% is. I think now it is, I think, visible, right?
Yes, sir. Yes, sir.
Okay. So, okay, anybody having any problem in understanding what I told you? First, all of you got the point that if the number of dimensions are increased, then the training samples, they are unable to represent, right, certain part of the spaces. So all of you got this point. You can put it on the chat, right? Because we may cover less, right? But I think whatever I'm covering, right, that should be understood by you. Anybody is having a problem in understanding the meaning of the dimensions? Okay, so what we'll do is we'll start again from the beginning, right? I will just cover the dimension, the reduction, the needs, right? Then, if possible, right, we'll cover the reduction techniques because there are a lot of reduction techniques, right? So first is all of you are aware of the meaning of the dimension. You can respond me on the chat. Okay, all of you know at least you have solved some machine learning problem. Say, anybody of you solved some machine learning problem like the classification? So more variables in the ML problem, right? So for example, you want to make the diagnosis, right, of the disease of the patient. How will you proceed? You require the symptoms. How will you put those symptoms in terms of data? So you require the symptoms, but how will you put those symptoms in terms of the data? So you will make the matrix, right? If there are these number of symptoms, right, and you are having the say k number of cases, right? So you will put the data in the form of k into d matrix, right? So each symptom will form one dimension, right? And if you are having the say 10 symptoms, then you can say that it is the 10-dimensional data, right? So that is the meaning of the dimension, that is the state of features, right? Or in the case of patients, right, number of symptoms, right, they indicates the dimension of the data, right? Now, if each symptom is of the nature 1, 0, means the symptom value is either in terms of 1 or 0. For example, if the symptom is fever, then you can say that the patient is having fever or not. If it is having the fever, you make it as 1. If not having the fever, you make it as 0. So if you are having these features, right, having the binary values, right, and you are having some 10 such features, then how many possible combinations that you will have, right, of the patients? Right, again I'm putting the problem in this way. If you are having the 10 features, and each feature is of binary nature, right, then how many possible cases of the patients that you may have? Right, so this is a very simple problem. Each feature is having the value 1 or 0, and you are having some 10 such features. Then how many possible features you may have? How many possible cases you may have? So it is 1024, right, at this time. Right? It is 1024. Right. All of you know that is got, right, this simple mathematics. Okay. And if the number of features are 40, then how many possible cases you may have? It is 2 raised to power 40. So that is a very huge figure. Right? It is a very huge figure. Right? Okay. Then we'll again come back to our 10 features problem. So the number of cases will be 1024. Right? And suppose you are having the training samples, right, of say the number, say 150. So you are having the 10 features, binary features, right? And you are having the data of only the 150 patients, right? Then how many cases they are not covered? So it is 1024 minus 150. Right? In terms of percentage, right, you are covering only the 150 by 1024 percentage of the cases. All of you got this mathematics? So I collected data of only 150 patients, right? But my total space is what? 1024. So in terms of, right, ratio, I have collected only the representation, right, of space in terms of percentage, and that percentage equals to 150 by 1024. So all of you got this simple mathematics. That means, what is the ratio in that case? 150 by 1024. How much is the ratio? It will be around 15%. Right? It will be around only 15%. It means what? Part of the space, right, that is not represented by the samples, right, or by the training data is going to be very less. And instead of now the number of dimensions as 10, if I increase to say 20, then this ratio will be still very less. Right? So any classification model that will build it on this very his data, right, tends to be more inaccurate. Right. So, in terms of geometry, this is put right using this equation, right? That is in terms of hypervolume of the cubes and spheres. So, cubes indicates the total space, right, of the dimensional data, right? And sphere, right, indicates some part of the space, right, in which the data is more concentrated. So this volume of the sphere to cube, right, it goes on or tends to zero as number of dimensions goes on. Right? It means what? The as dimension grows, right? Then your training data is not sufficient to represent all the part of spaces. Right? So that is the argument, right? Why you require the less number of dimensions. Right? So this is right. That is the less number of dimensions or the very high number of dimensions. Right? They may not be always useful to make the model more accurate. Right? So that's why you require the less number of dimensions. Right? Now, how you will then reduce the number of dimensions, right? Using some algorithm, right? That is based on the mathematical technique. And the mathematical techniques, they are going to exploit the dependency of one dimension, right, into another dimension. For example, if you are having the two symptoms, headache and fever, and all the patients, those who are having fever, they are also having the headache. It means what? The headache is completely dependent on the fever. And in that case, you don't have to take the headache as a dimension because it's not going to add any information required for the discrimination. So all the dimension reduction techniques, they are mainly exploiting, right, the dependency relationship, right, between the features. And this dependency can be a simple dependency like local or say the linear dependency. Like for example, if you are having the two features x1 and x2, so x2 is 2 times x1. That is a simple linear dependency, or it may be some non-linear dependency. Non-linear dependency means say x3 will be the x1 square plus 2x2. Okay, that is some kind of non-linear dependency. So all dimensional reduction techniques, right, they are mainly exploiting, right, this dependency relationship between the data. Anybody is having any problem now in understanding this? So who is having any problem, right? They can ask. Okay, Jaipal, Vinita, it is clear? Okay. Now, these are some techniques, right? They are categorized as the linear or non-linear technique. Right? So there is a lot of techniques, right, for damage reduction, and they are based on some mathematical proof or mathematical concept, right? And all they are exploiting the dependency, right, among the. So I will just cover, right, two of them, right, because it's not possible to cover all of them. But practically, you are having a very good Python library in the scikit-learn. So am I audible? Okay. So these are the techniques, right, for damage reduction, and they are based on some mathematical principles. Practically, you can use them very easily because the Python is having the good library, scikit-learn, right, in which you can use, right, all these techniques because there is a one-line statement, right, to make the damage reduction, right, in the Python. So all these are covered, right, in the scikit, except the one deep learning technique that is called as the auto encoding, in which you can use the TensorFlow, right? So either you can use the scikit-learn. So whatever I have put it here, most of them they are you can do it using the scikit-learn, but 8 and 9 you have to use the TensorFlow, right? Either. So these are the some points, right, of this basically. So PC is the principal component analysis. MDS is the multidimensional scale. So these are basically exploiting the your linear relationship between the data. So in the PCA, we try to extract relationship like the dependency of one feature on another feature or another set of features. Right? For example, suppose there are the three features x1, x2, and x3, and there is a relationship like x3 is twice x1 plus x2, then that can be exploited in the PCA. In the MDS, right, that is the multidimensional scaling, right? If you are in the high dimensional data, you are going to put that in the low dimension data so that the neighborhood relationship in terms of the Euclidean distance that will be preserved. So the meaning is if you have the 2 points, the d-dimensional space P1 and P2, and having some distance, say 10, in the MDS, right, we try to put them in the lower dimension so that the distance between the 2 points again it will be the similar to the 10. Right? So that is the multi-dimensional scale. Then you are having the nonlinear techniques, right, in which we are going to exploit the nonlinear dependencies, right, the data. And most of these nonlinear techniques, right, they are dependent on the concept of the manifold. Manifold, you can assume that you are having a thread, right, and in which you just put the dots. Right, you take a thread, right, straighten that thread and put the dots, right, on the thread, and after that you make the some shape like S, right, or you can make the some shape like say N, right? So you can make the different shapes, right, from the single thread, right? And then the points, right, which are far from the each other in the single thread, after say making the S or making the M, right, they may come near to each other. So in the Euclidean space, these points are near to each other, but as you traverse the thread, right, they are still having more distance. So this travels along the thread, right, it's called as the manifold. So there's nonlinear techniques, right? Most of them, they are going to preserve the distance in terms of the manifolds. So these are the LLU technique or Laplacian eigenmaps, right? So all our isomaps, they are using, right, this concept, and they are also widely used. Another techniques, right, which are used is in the deep learning. So or the neural network, right, in which what we'll do is, suppose you are having a very high dimensional data, then using the network, right, you can make a representation, right, or you can put a layer, right, so that number of neurons in successive layers this goes on decreasing, right, and after decreasing, right, after certain time, again you go on increasing the number of uh, neurons, right, in the layers, right, so then again they will come back to the original shape. So this can be done, right, using the deep learning, right, using the TensorFlow. And what we'll do is the input will be the same data and output will be also the same data. And based on that, we try to train the model. And once the model is trained, then the middle portion, right, of the layers, right, that can be used, right, for the reduced dimension, right, in the deep learning. So it is having the shape, right, just like what you can say, the funnel kind of network, or you just like hourglass. Right? That network is just like the shape of the hourglass. So these are some techniques, right? Uh, there are some points, right? How on which basis, right? These techniques are. Okay. Now this S curve, right? It is mainly used, right, by many dimension reduction techniques, right, for as a performance measure, right, or for testing the dimension reduction problem. So the performance measure here is the correlation, right? So the correlation is the distance of the points, right, in the original space, right, and then the distance of the points, right, between the new space. And higher is the correlation, more faithful will be the representation. You can see the or visualize them also, right? Uh, how they will look like, because this is the S curve is the your three-dimensional figure, right? And I put that two-dimensional, right, uh, representation. So you see that in the MDS, right, the blue color, right, we have the blue patch, right. But the colors are more separated, right, along the manifold, right. So if you traverse this S, right, then you will come across different colors, and you see that in the isomap, right, these colors are more, right, that color sequence is more visible, right. That's why you have more correlation, right, in the isomap. So these are again some results, right? And then there are some parameters, right, for the this demonstration problem, right? For example, in the LLE or HLLE, right, you are having the this distance calculation in terms of the neighborhoods. So this is done using the well neighborhoods, right? That's the history. Right? So we'll see right two methods right here, right, and then you will understand what is the meaning of this. So some techniques, and you see that there is no what you can say a single medicine, right, for all the data. For some data, you may get good results using the isomaps, right? But for some data, you may get very good results with the autoencoders, right? So many times you may have to apply the different techniques and get to see how these techniques can be possible. Then the another important thing, right, in the damage reduction techniques, apart from the performance measure, is the complexity. This complexity, this complexity is measured, right, using the n dimension, right? So if you are having the original data having the n dimension, then we say it is a n cube. It is taking the time, right? That is the proportion to the cube of the n. And in the LLE, right, you are having the additional p here. P is the number of target dimensions. So the n data is converted to n dimension data is converted to p dimension, right? So the formula p n square. Right? So it is something. Okay. Now we'll see, right, briefly the how these administrations perform. Right? And here first I'm taking the example of the principal component analysis, and then second example I will take as the linear local linear embedding. Now let's look at this data. Right? It is a two-dimensional data. Can you convert that data into a single dimension? So anybody can guess. Can you convert this data into a single dimension? You can just take the y-axis. Can you rotate this axis x1 and x2, right? So that, or you can make the projection on the diagonal. If you have the projection on the diagonal, right, that is between x1 and x2, right, then that means, or you can make the rotation of x1 and x2, right, then what will happen? So you will get the value only for one axis, and for other axis, right, you get values almost 0. So of course, suppose I will just have the diagonal, right, between x1 and x2, that is the one axis, and another axis is just the perpendicular to that diagonal. Right. So first I'm going to as the diagonal d1, and second I'm going to as diagonal d2. So on the d1, right, I will get some values, but on d2, right, I will get almost the 0 values. Right. And since all data they are having the value 0 on d2, right, it means I can scrap D2, and I'll just keep. All of you got this concept? You just have one diagonal axis, call it as the D1. Other axis is D2, that is just perpendicular to that, right? So if you make the prediction of these points on D1, right, you will get some values. But on the perpendicular axis like D2, right, you will get almost, right, so D2 you can scrap it, right? So that is how, right, you can transfer, right, this data from 2-dimension to single dimension, right, like this. So this Z1, right, Z1 is one axis. It is the diagonal axis. Now again, this is the your data reduction from 3 to. The question is, right, how you can make this transformation, right? So here the first diagonal, right, it is the D1, that is in between the kinematics is called as the first principal component, right? And the perpendicular axis, right, to this D1, right, is called as the second principal component. So this data can be reduced, right, to single dimension by taking only the first principal. Question is how we can do it mathematically. So these are some other steps, right, that you can use to find out these principal components. So what you have to do is you have to calculate the mean vector of the data. You have to calculate the covariance matrix of the data. Then you perform the calculate the eigenvectors and eigenvalues right, of the covariance matrix. Then you have to take the eigenvector corresponding to top eigenvalues, right? And then on these eigenvectors, right, you can rotate your proportional. So if you are having say the 10-dimensional data and you choose only the top 2 eigenvalues, so you will get the top 2 eigenvectors, and then you can project, right, the original points on the only 2 dimensions. Right. The covariance matrix, the meaning is like this. Suppose now this is the data, then you can say that you will have the positive covariance because that x is increased by this increase. And in the other side, right, you have if you is x, the y is decreased, right? Which is the negative covariance. And if there is no relationship between the x and y, then you will have the zero covariance. So covariance you can calculate, right, of the data, right? This equation. So this is called as the mean, right, of the data. Right? So the covariance between the 2 dimensions, j and k, you can calculate it. So if you are having the say the 3 dimensions, then your covariance matrix is also d by t. And once you get the covariance matrix, then if A is the covariance matrix, right, you have to calculate the eigenvalues of that matrix, right, using the standard eigenvalue equation. right? Second value equation that you have studied right in your engineering. So you will get the eigenvalues right of the covariance matrix. Then you can take the top eigenvectors corresponding to top eigenvalues. Right? So you get eigenvectors. And then you can project your original points on these eigenvectors. Get the representation in the lower dimensions. So each eigenvector is called as the principal component. And then the eigenvector corresponding to highest eigenvalue is called as the first principal component. So this is the principal component analysis, and it has been used right when there is a we have to expect a linear relationship of the data. But it cannot be used if there is a non-linear relationship, right? So for that, right, we'll use another algorithm that's called as the LLE. It is a local linear regression. First, we'll see how this algorithm works. So this is again based on the concept of manifold. First, you see what is the meaning of the manifold. You just now look at this figure. Right? If you traverse, right, this score from 0, 1, 2, 4, 5, 6, 7, 8, right? So this is the manifold. Right? Now, what is the distance between the point 0 and 10? So in the Euclidean space, right, this distance is less. Right? The point distance between the 2 points 0. But it is on the manifold, right? This distance is very large because if it starts say from the 0, then you put the 1. So in terms of manifold, right, the distance between the 0 and 10 is going to be very large. Right? So that is the concept of manifold. Okay. So in the LLE, we try to preserve the distance of the that is calculated, right, on the manifold. We are not going to preserve Euclidean distance. We are going to preserve the distance of the manifold. So how the LLE operates? So in the PCA, you take the distance or the covariances, and you try to model your distances all the data points, right, between each other. But in the LLE, we just try to preserve the neighborhood distances. Means if the point is 1, then we try to preserve the distance of 1 from its neighbors like 0 and right? But in the case of PCA, right, the distance from 1 to 10 will also matter. So 10 is far away from 1, right? But in the PCA, right, this also matters, right? It is 1, right? But in the case of LLE, we just try to serve the neighborhood distances. Now the algorithm works like this. Suppose we fix it, the number of neighbors, right, as say k. Then what we'll do is for each point we'll calculate the k neighbors. Right? So for each point we calculate the k neighbors. and we try to express the point, right, using the k levels, right? So this is the expression EW, right? So this is the distance, right, of the point, and if the representation of the point in terms of the k levels, right? So this is called as the reconstruction path. So if the number of members are k, right? So for example, suppose I choose that okay, we have the two neighbors. Then for one, right, you will get the two neighbors as 0 and 2. So we will try to express, right, one in terms of the neighbor. Okay. And then one is having its original coordinate, right, and then you have the representation. So the reconstruction error is the original point and its representation, right, their difference. Right. Then for each neighbor, right, we determine the weightage. If the point is, suppose there are the two neighbors, but one neighbor is very near, it is having the high weightage, and another neighbor is having the low weightage. So you will have the weightage calculation, right? We'll see, right, how it is done, right? So, and then you will have the again the representation in the lower dimensional space, right? And we try to have the this representation, right, similar to your original d dimensions. So this is actually the mathematical proof, right? We'll not go into that, but we'll just see the first result and then we'll see the exactly how the calculations are done. So this is the LLE output and this is the PC output. Right? So if you see the PC output, the distance between 2 and 3, right, is going to be very far, right? But in the case of LLE, right, it is near to each other, right? And near to. So along the manifold, right, the distances are more preserved in the LLE as compared to. So just see the calculations, right, how it is done, right? So this is example. So this is a 4-dimensional data and there are 4 points, right? And we'll fix that the number of neighbors will be 2, right? So that is the first. Okay. Then for each point, we'll calculate the distance of every other point, right, using the Euclidean distance formula. So you will get this distance matrix, right? And then we'll choose the say 2 nearest neighbors for each point. So for x1, the points 2 and 4 they are near to each other. For x2, the points 1 and 4 they are near to each other. And for x3, right, the points 4 and 2 they are near to each other. Right? So we'll have the nearest neighbors, right? If case 2, then we'll take the 2 nearest. So first is the calculation of the distance matrix, and second is the using the k neighbors, right, and express, right, S of the neighbor. Then you find out the difference matrix for each point. For example, x1 is 3215 and its nearest neighbors are 4632 and 3579. So you'll get the difference matrix. And then we have the gram matrix, what we call it as the gram matrix, that is the difference matrix into different transpose. So that is the G1 matrix. And then we calculate the slow inverse, right? B1. Get the weightage of each neighbor. So normally this is done, right, so that nearest neighbor, right, will have the more weightage than the other neighbors, and all the weightages, they are summed to B1. So the weightage for each point, right, that will be, if you make the sum, that will be 1. So then you will get a weight matrix, right? You will have the weight matrix right from the data. And then we'll calculate the M matrix, that is the identity matrix minus W matrix, and where I is identity. We get the M matrix, and then we'll find out the eigenvectors and eigenvalues. Then you choose the eigenvalues, right? You sort them in the increasing order, right? And you take the minimum eigenvalues, right? The first eigenvalue will be given because that is corresponding to 0, right? So that you do. And you will get eigen vectors, right, corresponding to lower eigenvalues. So if you take the p eigenvectors, then it is the three-dimensional representation of the. So these are the mathematical steps that you have to, right? So you can have the Python code that is given in the circuit library. You can manually also check this. So this is the manual code that is. And then you can use the three-dimensional data. So this is the manifold, right, of this data, and you see that the colors, they are quite resolved, right in the right. This is again the phase data, right, and you will see that the similar phases, they are near to each other in the two dimensions. So if the image is of the size, say 30 by 30, then it's the 900 dimensions. And now we are showing that this is regular dimension. And you see that similar faces, they are near to. So you can easily replace this data. Right? Here again it is the example. In the PCA, right, how these faces are mapped. Right? So they are having more better mapping, right, in the case of me. So generally, right, it is the manifold based learning or the dimension reduction technique, right, which preserves the distances, right, in the manifold. Right. Uh, you can use the other techniques also, right? In the scikit-learn, you will have I think the internet was having some breakdown. Now it is audible.
Yes, sir.
Actually, what is happening is that due to this power problem, because today is the Wednesday, right, and there are intermittent shutdowns, right, from the electricity, right. So our switches and routers, right, in the department, they are having the power challenge. So the PPT is, I think, visible to all. I will just repeat daily steps, right, using this example again. If it is breakdown, right, you just call me Jitendra, because I'm not using this mobile frequently.
Ye-
Right?
Yes. Sorry.
Okay. So this LLE, it is based on preserving the manifold distances. Right? I think we were up to here. Right? So this is the LLE technique, and you'll see compared with the PCA. Yeah, if you compare the distance between the two entry, right, in the original space, in the PCA, right, you'll see that the distance between two entry it is shown very large, but in the LLE, right, it is comparatively it is better. Right. So LLE basically it preserves the distances, right, of the manifold, right. Manifold distances means if you start from 0, 1, 3, right, this is the traversal of the manifold. Right? So 0 is far away from 10, right? Manifold, right? So that is LLE try to preserve that. So in the LLE, what is done is that we are going to have okay again. So I think am I audible or not audible?
You're audible.
The LLE, what we do is that we try to preserve only the neighborhood distances, not all distances. Right? So once you say 1 is the neighborhood of 0, so we try to preserve the distance between 0 and 1. We are not going to bother about preserving the distance between 0 and 10. They are far from each other. Right? But the PCA, right, it is basically global in nature. We try to preserve the distance between 0 and 10 also. Right? So that's why the PCA may not be useful, right, when we are having the data like this. It means having the curvatures or something like that, right, of curves, right. This will not perform much, right. So how this is done, right, is the simple, these are the mathematical steps. So we are having originally this data, we are having the 4 points and number of dimensions and so forth, and we'll use the two dimensions. The first step is that we'll calculate the distance matrix, distance of one point from each other point. So using the Euclidean distance, right, we can get the distance matrix. Then we decided that okay, we will do this algorithm with the k equals to 2 neighbors, right? If you take more neighbors, right, you will have more calculations. Of course, this number of neighbor decisions, right, it is a subjective decision. And then for each neighbor, you calculate the difference matrix. For example, x1 is 3, 2, 1, 5, and its neighbors are 2 and 4, then you will get the difference like 4 minus 3, then 6 minus 2. So you get a difference matrix. And then we calculate a gram matrix, right? That is difference transpose. and then you calculate the slow inverse of it to get a weightage of each neighbor, right? And that will form the what you can call the weight matrix. Normally, the weight matrix, right? It will see the row-wise summary, row-wise sum, right? It will be 1, right? And if the neighbor is more near, then it is having more weightage. That is the weightage calculation. And then you calculate the M matrix, right? That is the I minus W where I is added, right? And then you calculate the eigenvector of this M matrix, and then you'll choose the eigenvectors, right? Having the lower eigenvalues. Of course, the first eigenvalue will ignore, right? And we take the other eigenvectors, right? So if you decide that we want to map it into 2 dimensions, then we'll ignore the first eigenvector and we'll choose the next 2 eigenvectors, right? So that is the lower representation, or sorry, the representation of lower dimensions. This is the Python code that you can directly use, the LLE code you can directly use from the cycle. And this is the example, right? You start using this, and you take just see here that colors, right, on each part, and you see that once you unfold this manifold, right, you will get a similar figure. So originally this data is in the 3-dimensional space, and if you roll out it, right, in the LLE, right, you get a 2-dimensional. So this is the LLE algorithm. It is widely used, right, as compared to PCA, right? This LLE is used because it preserves the basically the local geometry, right? So we'll stop. Anybody think any doubt?
Participants, if you're having any queries, any doubts, you can raise your doubts here.
Okay. So we'll stop.
So thank you very much, sir, for your session, dimensionality reduction. So if any queries comes from participant side, I will going to you so that they can get their question answered. So thank you for your valuable time, sir, at this point.
Okay, thank you.
Okay, thank you, sir.
Okay.
So participant will have a break at this point, and 12 o'clock we will going to join for the next session, which is based on introduction to machine learning. So you can take a break at this point.